Welcome back everyone. In this class, as I promised, I will actually do these isomorphism theorems. Okay. So, let us actually briefly recall what we did in the last class. Okay, that will help us actually to get into this isomorphism theorems. Okay. So, we defined what is called quotient algebras using these ideals. Okay. So, what is ideal? So, ideal is a subspace, okay, a subspace satisfying the following property, bracket x y should be inside I for all x in G and y in I. Okay. So, then once given ideal I inside G, so one can look at this quotient space. So, which is all these translations of this I by elements of G. Okay. So, then we defined a Lie product using the Lie product of G, the bracket x plus I and y plus I. So, this was defined to be the bracket x y plus I for all x y inside G. Okay. So, we saw that we verified this G modulo I is actually a Lie algebra with respect to this induced product, and we also saw that this quotient map which we denoted by pi. So, which is actually from G to G modulo I given by x goes to x plus I, this is actually a Lie homomorphism. So, since this is a Lie homomorphism, we also calculated the kernel. The kernel is obviously being kernel, the ideal that we started with. Okay. So, we also proved one simple fact. So, what is that fact? So, if J is another ideal, okay, containing G, so then we can talk about this J modulo I. So, which is a subspace of G modulo I. So, this is indeed ideal inside G modulo I. Okay. So, these are all the facts that we already proved. So, now what we will do? We will actually use all these facts and then prove our isomorphism theorems. Okay. So, you must have seen these isomorphism theorems in various different places. For example, in group theory you must have seen these isomorphism theorems, in ring theory and even for the vector spaces you must have seen. So, whenever you change this category of objects in of course, the algebraic objects, these isomorphism theorems will be applicable for them, and then you can actually use them to actually kind of say something about the quotient that you actually produce. So, these isomorphism theorems are very important in identifying what will be the quotient algebras in general. Okay. So, for this reason, okay, I would like to go slowly and then explain you what are these theorems, and more or less what you have seen in vector spaces. Okay, the same proofs will go through, but every time whenever the some maps or something makes sense, you need to verify whether it is Lie algebra homomorphism and so on. Okay. So, once that verification is done, okay, remaining thing will be obvious from the arguments that you see in linear algebra. Okay. So, let us first start with this first isomorphism theorem, which is actually a fundamental theorem. Okay. So, this theorem is indeed mother theorem for everything. Okay. There are three theorems. Okay. This is the very first theorem. Using this theorem, all other theorems can be obtained. So, what is this theorem about? This actually theorem says about what we can expect about the quotient algebra. So, if you start with a Lie homomorphism, okay. So, here is the first theorem. So, here is the statement. So, let G1, G2 be two Lie algebras over complex numbers, okay, and let us say phi is actually a Lie homomorphism from G1 to G2. So, this is a homomorphism, not just a C linear map, this is actually a Lie homomorphism. So, then what we can prove? So, we already verified for given homomorphism the kernel of phi is an ideal. Okay. So if this is the data, so then what we can conclude, the kernel of phi must be an ideal inside G1, and not only that, this image of this phi. Okay, what is that? This is those phi of x coming this x coming from G1. So, this set. So, this is a subalgebra of G2. Okay. So, not only that, moreover, when you take this quotient by this kernel, this G1 modulo the kernel, we know from vector spaces that G1 modulo the kernel must be isomorphic to G2 as a G1 modulo the kernel must be isomorphic to the image phi as vector space. But now we are dealing with all this Lie homomorphism and so on. So, in this category, so G1 modulo the kernel will naturally become isomorphic to the image phi as Lie algebras. Okay. So, what does it mean? There will be a natural quotient map from G1 modulo the kernel phi onto this image phi, which will be isomorphism. Okay. So, now we will prove this. Okay. All we need to do is we just need to actually construct this quotient map, okay, natural induced map, and then after that we need to verify. Okay. So, more or less once we know what is the natural map, it is easy to verify, that will be bijective isomorphism. Okay. So, let us construct that quotient map and then verify the details. So, what is the natural map? Let me call it phi tilde. So, the phi tilde. So, these two things are I am actually skipping, the kernel phi being ideal, which we have already verified, and it is not hard to verify. Image phi is actually a subalgebra, because phi is a Lie homomorphism. Phi of bracket x y will be equal to bracket phi of x phi of y. Because of that, it immediately implies image phi is actually a subalgebra. So, subspace is obvious, because image of a subspace must be subspace. So, this fact is also I am just leaving it. Now, we will just focus on the quotient map, and then we will try to prove that is actually bijective homomorphism. So, what is the quotient map? Natural induced map. So, this is G1 modulo the kernel phi to image phi, we are going to define this map. So, what is this map? Obviously, phi 1 tilde of x plus kernel phi, you define it to be just phi of x. Okay. So, that is the natural induced map from G1 modulo the kernel phi to image phi, okay, which is sitting inside G2. So, this map is well defined. So, that you must have seen in first question linear algebra, or it is not that hard to verify this map is well defined. So, let us verify. So, if you take two cosets representatives, call it x and y, then we know that. So, this will imply x minus y should be inside kernel phi, but this will imply that phi of x minus y must be 0. So, that means phi of x must be equal to phi of y. Okay. So, this says whenever you start with two representations from one coset, the images are equal. So, that means this phi tilde must be well defined, and you can also trace back these steps. If phi of x equal to phi of y, then that would imply phi of x minus y equal to 0, and that would imply x minus y is in the kernel phi, and that would imply the cosets corresponding to x and y are same. So, that means this one thing proves, okay, that phi tilde is well defined and bijective, because we have actually restricted ourselves to image of phi. Okay, we do not care about this G2. So, the map is already surjective. Now, this star implies this map is injective. So, it is bijective. So, now you have bijective map and it is not hard to prove, it is a linear map, okay. That is already must have verified in the linear algebra course. So, I will just leave it as exercise. So, now you have bijective linear map which is invertible linear map, okay. So, now all we need to verify, you have two Lie algebras, one is on the left side, another one is on the right side. So, if you verify this linear map is actually Lie algebra homomorphism, then we are done. Okay. So, let us verify this map is Lie algebra homomorphism. So, you start with two elements x y inside G 1. Okay. So, that means we are looking at the cosets, okay, the bracket x plus I, y plus I. So, now what we need to prove? We need to prove that this should be equal to phi of bracket x plus y, y plus I should be equal to bracket phi tilde of x plus y and phi tilde of y plus I. Okay. So, what does it mean? You just rewrite this in terms of the maps. So, this is nothing but phi of x and this is nothing but phi of y on the right side, but on the left side this is just phi tilde of bracket x y plus I, nothing more. But by definition, what is phi tilde of bracket x y plus I? So, which is nothing but phi of bracket x y. Okay. But phi is actually Lie algebra homomorphism to begin with. So, phi of bracket x y will become phi of x, phi of y bracket. So, that means we verified that phi tilde is a Lie homomorphism. Okay. So, this is what we wanted to verify. So, this is same as this. Okay. So, now this implies phi tilde is a bijective homomorphism. So, that means it is an isomorphism. Okay. So, this is actually a very good method to identify what will be your quotient Lie algebra. So, the quotient Lie algebra, as long as you can establish this Lie homomorphism from G 1 to some known Lie algebra, and if you can actually identify the kernel with the ideal that you start with, then you can identify this quotient with that subalgebra of that known algebra. Okay. So, that is how one can identify the quotient. So, for example, we have this odd map, okay, the adjoint map from G to GLG. Okay. See, this G is to begin with abstract Lie algebra. Okay. So, this is an abstract Lie algebra. But what we have on the right side is actually more concrete Lie algebra. What I mean by concrete? This is actually G is a vector space. So, if you know the dimension, so this is the general linear Lie algebra, it is a very particular example. Okay. So, you can do computations everything in this GLG, but for abstract Lie algebra we do not know how to do computations. Okay. But here we can do the computation using the commutator brackets. So, that is what I mean by concrete Lie algebra. Okay. This is general linear, okay, Lie algebra. So, suppose this G, if it becomes isomorphic to some subalgebra of GLG, then we can actually do lots of computations. So, that will be useful. But the thing is it is not always true. Okay. Actually, it is true for finite dimensional Lie algebras for complex numbers. So, but anyway, it is not true in general for any Lie algebra that G can be like embedded inside some general linear Lie algebra. Okay. But here in this particular map, which is like a God given map for us, this is the adjoint map. So, this adjoint map actually kind of embeds G modulo the kernel of adjoint map. But what is the kernel of adjoint map? the kernel of this adjoint map, it is those x in G such that add x is 0, but add x is 0 means what? Add x is 0 on G. So, that means this is those x in G such that bracket x y is 0 for all y in G. Okay. So, this is a very special ideal inside your Lie algebra, which is called the center. So, the center of G. Okay. So, this if you take this adjoint map, the kernel of that adjoint map is the center. Okay. And what one can actually prove immediately using the first isomorphism theorem, this G modulo the center, usually the center we will denote it by Z of G. Okay. So, this is the definition of the center. If you go modulo this center, then this is sits inside. Okay. This notation means injective map. Okay. Sits inside GL of G. So, modulo the center, you can actually embed any of this Lie algebra inside this general linear Lie algebra. But here we are actually talking about very particular general linear Lie algebra. Okay. So, here I will recall what is called Adot's theorem. If I get time later during the course, then I will actually give a proof of this Adot's theorem, but I do not want to promise anything now. So, what is this Adot's theorem says? If you start with finite dimensional Lie algebra over complex numbers, then there exist n in n such that this G can be embedded inside GLN of C. Okay. So, that means any, so all these subalgebras of GLN of C, they are called linear Lie algebras. Okay. So, this Adot's theorem proves any abstract finite dimensional Lie algebra can be realized as linear subalgebra of some general linear Lie algebra. So, why you want to do this? Because here we can do very explicit calculations. So, here very explicit calculations are possible. Okay. So, here this is just abstract Lie algebra. So, we do not know like what we are doing. So, that is why this Adot's theorem is actually very important thing. But anyway, I will just state it here and then like we will see later whether we can prove or not during the course. So, here yeah. So, now we will see a class of Lie algebras. So, for which the center will be always 0. Okay. So, that class is called semi-simple Lie algebras. Okay. Semi-simple Lie algebras. So, we will actually give the definition of semi-simple Lie algebras later in this course, but this for this class one knows that center of this semi-simple Lie algebras always 0. So, that means if you use this add map, this add map will be always injective. Okay. So, that is always gives you embedding inside GLG for this particular semi-simple Lie algebras. But anyway, we will come to that later. Just I wanted to point out this. Okay. So, now we will go back to our isomorphism theorems and then see what other isomorphism theorem says. But before that, let me just give you one other example. Okay. For example, what I can do, I can take this GL and C and then we can actually take this trace map. Okay. So, what is this trace map does? Okay, you take x and then you send it to trace of x. And it is not hard to see this is actually a Lie algebra homomorphism. Why? Because on the right side you have one dimensional space. So, it must be abelian, and the Lie structure that I have already explained, that is the abelian structure. But anyway, on the left side you have a commutator bracket, but if you take trace of any commutator bracket, that will be 0. Okay. Because of that, this map trace, okay, is actually a Lie algebra homomorphism. Then what is the kernel of this trace map? The kernel of this trace map is nothing but those x in GL and C such that trace of x is 0. So, which is nothing but SL and C. Okay. So, then using the first isomorphism theorem, we see that this GL and C modulo SL and C is nothing but isomorphic to this one dimensional abelian algebra C. Okay. So, this is example 2. We will see later some more examples, but anyway we will stop with this particular example. So, now what I want to do, I want to actually prove this second isomorphism theorem. Okay. This is the theorem 2. So, this is all can be written as part of one theorem, but anyway I am just calling it theorem 2. So, now what it says, this is actually tells about if we start with two ideals I and j, then there are various algebras ideals that can be constructed, and then this theorem actually gives you relationship between these obvious algebras and the quotient algebras. Okay. Let us now start with I and j, both are ideals inside G. Okay. Then we have already seen that I plus j is an ideal. Now, you can actually take I plus j, now go modulo j. Okay. So, we will actually prove that. So, that means what? J is an ideal inside. Okay. So, then, so let me write it as a part of the theorem. So, then j is an ideal inside I plus j, and I intersection j, that is also ideal inside I, and moreover, okay, we have, so we can talk about the quotient now, I plus j modulo j. So, that must be isomorphic to I modulo I intersection j. Okay. So, this is the main part of the theorem. Okay. It is not hard to prove that j is ideal inside I plus j. Okay, that I just leave it to you to check, because j is already ideal in G. So, it must be ideal in I plus j. So, that is obvious, and similarly I intersection j will be ideal in I. Okay, both are easy to verify. So, this part I will just leave it to you. Now, I will just check only that I plus j modulo j is isomorphic to I modulo I intersection j. So, how do I prove this? So, basically you start defining a map. So, you have this map from I to I modulo I intersection j. Okay. What is this map? You can take x and then send it to x plus I intersection j. There is no harm, this is a quotient map. So, now what you do, you can also like define this another map. So, from I plus j to this I, you just define kind of projection. Okay. Maybe actually I can do the other way, that will be easier. Mainly we need to use this first isomorphism theorem. Okay. So, you define from I to I plus j mod j. What is the map? You take x, you just send it to x plus j, and this is a well defined map. Why? Because if x plus j is equal to, so what do we need to verify? This is just obviously well defined. Okay. There is nothing to verify. So, this is a well defined map. This is actually a C linear map, that is also obvious to verify, and this is actually Lie algebra homomorphism. So, that is also obvious, because phi of x y is nothing but bracket x y plus j, which is nothing but x plus j y plus j So, that means this is phi of x, phi of y. Okay. So, that verifies that this is Lie algebra homomorphism. Okay. Since the elements of I plus j looks like x plus y for some x in I and y plus y in j. So, if you take some typical element inside this I plus j modulo j, then you can see that this is same as x plus j. Why? Because y is in j, since y is in j. So, that implies phi is surjective. So, there is no need to actually, there is nothing to check. So, this is a surjectively algebra homomorphism. Now, what is the kernel? So, the kernel, if you can identify, then the I modulo the kernel phi will be isomorphic to, because the map is surjective, I plus j modulo j. Okay. But the kernel, if you look at it, this is those x in I such that phi of x is 0, but what it is, those x in I such that phi of x is x plus j, which is 0 means that should be equal to j. So, that is just those x in I such that x is in j. So, that is nothing but I intersection j. So, by computing very explicitly the kernel, we see that I modulo I intersection j is isomorphic to I plus j modulo j. Okay. So, this is somewhat immediate from the first isomorphism theorem. So, now let us look at this third isomorphism theorem. Again this is actually relates ideals, okay, but it is actually kind of second degree construction. So, the first construction is the quotient. Now, we can talk about quotient of quotients. Okay. So, one wants to understand what will happen if we do quotient of quotients, but this third isomorphism theorem says the quotient of quotients will be again a quotient. Okay. We will not actually get anything new if we do this quotient of quotients. Okay. So, let us see what we really get. So, we take I, j, they are ideals inside G. Okay. This is the theorem 3, and then you assume that I is contained in G. Okay. So, now what we can talk about? So, we can talk about the following quotients. This G modulo I, so that is actually a quotient algebra. We just saw as from our previous results, this is actually J modulo I will be a subspace of G modulo I, but we proved that it is indeed an ideal inside G modulo I. Okay. So, this is the setting, let such that. So, then we have this. Now, furthermore, okay, moreover, what we can do, we can construct this G modulo I modulo J modulo I. Okay. So, this is what I call quotient of quotient, but indeed what happens, this quotient of quotient becomes isomorphic to just G modulo J. Okay. So, this is just a quotient, we are not getting anything new. Okay. It is in some sense this I and I gets cancelled. Okay. You can remember that way, but this is what one gets. Again, to prove this, what we do, we just construct one Lie algebra homomorphism from G modulo I to G modulo J. So, construct like let me call it some F Lie algebra homomorphism, okay, maybe surjective, okay, surjective. So, then if you say the kernel of f is j modulo I, So, then we are done, using first isomorphism theorem. Okay. So, that is what we will do. So, then how do you construct f? So, there is a natural map, that is what you take. You take G modulo I to G modulo j. So, what is the map? Here it is x plus I, you just simply send it to x plus j. Okay. So, only thing we need to verify whether this map is well defined or not. Okay. So, that is easy to verify, because if x plus I is same as x dash plus I, that will imply that x minus x dash is in I, but I is contained in j. So, that will imply x minus x dash is in j, but that will imply x plus j must be equal to x dash plus j. So, because of this we get f of x plus I is same as f of x dash plus I. Okay. So, that says it is well defined. So, now let us see, once it is well defined, I will leave it to you to check. This will actually define C linear map and Lie algebra homomorphism. Indeed, there is nothing to check, only important thing to check is it is well defined. All remaining thing will follow from like the way we defined. Okay. So, now let me just compute the kernel and then convince you that the kernel is indeed j modulo I. So, what is the kernel? The kernel is those x plus I such that when you apply x plus I, then that must be 0. Okay. But what it is? This is those x plus I such that this x plus I, which is the image is nothing but x plus j. So, that x plus j should be equal to j. So, that means what? This is those x plus I such that x is in j. So, that is just j modulo I. Okay. So, it is immediate computation that the kernel of f is nothing but j modulo I. So, that means the g modulo I modulo the kernel will be isomorphic to g modulo I. This is obviously surjective, because given any x plus j, you have x plus I as a pre-image. So, that implies that g modulo I, the modulo the kernel, which is j modulo I, is isomorphic to g modulo j. Okay. So, this is actually kind of ensures that you do not need to go like quotient of quotient and so on. Okay. This procedure somewhat complete once you take the quotient. So, there is no iteration. Okay. You will not get anything new out of it. Okay. So, the important thing is like one should cleverly use these theorems. Okay. That is really important. Okay. For example, I will just tell you like the way one uses in practice. So, what we want to do, okay, suppose you are given ideal I and then the Lie algebra G, okay, let us say this is given. So, what we want to do, we want to identify what is G modulo I. Okay. So, G modulo I quotient algebra is defined abstractly, but it is important to actually understand very explicitly what it is. Okay. Sometimes that helps concretely, if we can actually identify it with something, then it will help. So, because quotient is like very tricky thing. Okay. There are many ways to like define quotient. Yeah, sorry, that means like you can start with any ideal and then define quotient, but unless you actually identify it with something else that is somewhat handleable, then there is no point in working with quotient. Okay. Abstract way it is good, but concrete identification somewhat helps. But how do you concretely identify with something? So, find another known algebra, call it G dash, and look for this map F, which is a Lie homomorphism, which is from G to G dash such that the kernel of f becomes I. Okay. So, that will imply G modulo this I is embedded inside. Okay. So, this is isomorphism which is sit inside G dash. Okay. So, I am not claiming that given I you will be able to always find this G dash such that which looks nice such that this G modulo I can be embedded in G dash. But if you are able to do that, then computations about all this G mod I becomes somewhat easier. Okay. Assuming that this G dash is actually somewhat well known algebra. Okay. So, I will stop here and then I will actually continue in the next lecture with some other constructions like direct sums and so on. Okay. We will then once we develop enough these basics, we will move on to some particular classes of Lie algebra called solvable Lie algebra, nilpotent Lie algebras, semi-simple Lie algebras, and then see some of the basic properties of them, and then we will use those important informations to study the structure theory of semi-simple Lie algebras. Okay, I will stop here.